All right. Good morning, everyone. I think we'll get started. We'll have exam tomorrow. Okay. So if you are not in quarantine, you need to come to the class for the exam tomorrow. Okay. And then starting from tomorrow, you'll see your homework number 10 will be online available for you to work on. And that's due a week from tomorrow, Wednesday. Okay. And I'll probably put we'll after the homework number 10, we'll have two more assignments. I will probably put those two up in the coming days. Okay, so keep a look on those two assignments to be out there. All right, so let's get started on the lecture for today. Yesterday we started chapter 15 on the AC circuit. So basically, most of the time we are using AC sources. So that means your voltage, it's alternating between positive and negative values. Okay, so you can use a sine function or a cosine function. In this text, we are using sine function here. So your V has a peak value V0 and then times the sine of omega t, where omega is the angular frequency, which is 2 pi times the frequency. And if you have a resistor in the circuit, then I is also a sine function with a maximum of I naught. Okay, we check on that as well. When you have a resistor in an AC circuit, then the peak of the voltage and peak of the current, they happen at the same time. So we call them to be in phase. They are having the same sine function. Okay. That's called when they peak at the same time. It's called in phase. So that means they in the argument of the sine function, there's no phase differences. Okay. All right. So because we are using a sine function or cosine function for the AC voltage and current, then if you do average of them, it will be 0. So root mean square quantity is more useful here to describe the powers as assumed for the elements. So root mean square quantity quickly review is for the root mean square quantity is equal to 1 over square root of the maximum value. Okay, if you have sine or cosine function. All right. So we took a look for the power consumed by resistor in AC circuit. Then it's if you use root mean square quantity, power is equal to the root mean square current square times R, or you can write as the root mean square voltage square divided by R. Or another expression is to use the V root mean square times I root mean square. So basically, those are similar expressions when you're using the just V square over R, I square times I, and V times I when we have a DC circuit. Okay. In the case if you have an inductor in the circuit, then if this is AC source, then the current is changing. So then there's induced voltage in that. In that case, if you apply voltage as a sine function, then the current is a cosine function because you are doing derivative to the sine to the voltage over dt. Okay. And then you can rewrite the cosine function as a sine of omega t minus pi over 2. Okay, so in that sense, when you plot V and I in the same graph here, you'll see that the current in this case is leading the voltage. So that means current peaks first before the voltage peaks. Okay, so for the current peak is equal to, in this expression, you can see is equal to V peak divided by omega L. Then in this case, we call omega L to be the reactance of the inductor to the AC source. So this is called inductive reactance XL equal to omega L, and that has SI unit of ohms. The electric power in an inductor, it turns out to be 0 when it's supplied with the AC source. Okay, so that means it doesn't consume power. On the other hand, if you have a capacitor in AC circuit, then this time again because you have I that is equal to derivative of V over dt. So if you do that, you'll see that it's again a cosine function. In this case, it reacts to the AC source differently. When you have just V equal to 0 and start to go up, actually the current here start with maximum value. So you can imagine this is like a charging process. When you are charging it, your current goes down. When it's fully charged, then your current goes to 0. Okay, so in this case, it's a little bit different. So your current is leading the voltage by 90 degree. Okay, I think I probably mentioned it wrong for the inductor in a couple of slides back. For the inductor, the voltage leads the current. Okay, and in this case, the current leads the voltage. Okay, by 90 degree or pi over 2. So take a look on the expression for the current. It's omega C VC peak. So then if you rewrite this I peak as VC peak divided by 1 over omega C. So this is called the capacitive inductor reactance. Okay, so XC equal to 1 over omega C. So in this time for capacitive reactance, it's inversely proportional to the frequency. Omega again is the 2 pi times F. Okay. And we look at we took a look on the power consumed by a capacitor in an AC circuit. It's going to be 0. So that means in an AC circuit, the capacitor doesn't consume power. All right. So today we are going to take a look on the concept of called phasor. So this is kind of something similar to vector. So the phasor is defined as vectors whose length is the maximum voltage, okay, or current, and it rotates around the origin with the angular speed of the oscillation current. So angular speed will be the 2 pi times f, okay, in that case. So it's the angular frequency, the same angular frequency will be your angular speed here. So it rotates in that fashion, okay. So then at any instant, the value of voltage or current then would be its projection of this vector on the y-axis. Okay, so in this case, you can see the green here, green vector here is your maximum Imax vector. Okay, it's rotating with omega angular velocity there in that fashion. So then its y projection will be Imax sine omega t. Okay, and then for the voltage, this vector over here, maximum vector here rotating with the omega here, the y projection will be V max sine omega t. Okay, so then you get the voltage as a sine function. It's the y projection. I is also the y projection. So if I max vector and the V max vector, they are having the same directional angle theta, so that means they are in phase, right? So they are the same sine function, okay? So this would then refer to the phasors of, so the phasor of voltage and the phasor of the current for a resistor in an AC circuit, right? Now, on the other hand, if you have a capacitor in an AC circuit, then you can represent its voltage phasor and then its current phasor. So it's a V max and then the I max in that case. For a capacitor in AC source, we know that the current leads by 90 degrees. So then this I max phasor will be perpendicular to this V max. Okay, so that's that thing there. Then if you look at the Y projection of I max, it's going to be, so this is the theta. If this is the theta, theta is the directional angle for I max, then this guy will be equal to theta minus 90. Okay, so your current leads the voltage by 90 degree in that case. All right. Now, if you have a RC circuit, then the current across the resistor and the current across the capacitor, they are not in phase, okay? So that means the maximum current is not the sum of the maximum from the resistor plus the maximum from the capacitor. Okay, so in that case, they are the two phases will have a 90-degree angle. So we can take a look on here. So this is the Imax, all right, on the resistor. Okay, so then the Imax times R will be the voltage on the resistor. Okay, so this is the voltage on the resistor. And then the voltage on the capacitor will be Imax times XC. So this will be the voltage phasor for the capacitor. Okay, so you can see voltage on the resistor and then voltage on the capacitor, they are having a 90-degree angle. So then the sum, because you treat them as vector, so then you'll be doing vector addition. So then the sum will be for the maximum for the whole circuit is going to be this guy, which is equal to square root of the Imax R square plus the Imax XC square. Okay, and then you can see the Imax is the same. You can single that out to be in front of the square root. So then it's Vmax is equal to Imax times square root of R square plus XC square. So in the square root here, this happens to be the impedance of the RC circuit. Okay, so that's Z. So then this is equal to Imax times Z. Okay. All right, so that's for a RC circuit. So in this case, if we use Z, the impedance, then V is similar to the Ohm's law, which says V equal to I times R in this case, because impedance will be the replacing R. So then your V max is going to equal to I max times Z. Similarly, if you're looking for V RMS is equal to I RMS times Z, okay, in this case. So that's the impedance of an RC circuit is R squared plus XC squared, where XC is equal to 1 over omega times C. And then again, omega is 2 pi times F, the frequency, okay? Now, the angle between the voltage phasor on the resistor and then the overall phasor for the whole circuit for the voltage. So this is theta. If you do cosine of theta, you will find that cosine is adjacent divided by hypotenuse. So it's I max R over I max Z. I max and I max will cancel out. So then that will be equal to R divided by Z. Okay, that gives you cosine of this angle phi. All right. And if you look at the power consumed by this circuit, so then the power consumed by the circuit should be just the power consumed by the on the resistor, because this capacitor does not consume any power. Okay, so IRM squared times R will be the power consumed by the resistor, and you can write one of the IRMS as VRMS divided by Z. So then power is equal to I RMS V RMS times R over Z, which in the previous case, you can see R over Z is cosine of phi. So then this factor cosine phi is called power factor. That tells you how much power is consumed. So according to the VRMS and then times the IRMS, because you are not consuming 100% of the power, okay, that provided by IRMS times VRMS in the case if you have RC circuit, okay. Now, if you just have a resistor, then it's equal to this guy, okay. All right, because in that case, then that will be 100%, okay, because that's the only element, okay. Now, the other element doesn't consume power, so then it's not 100% of I RMS times V RMS. All right. So we'll take a look on one example here on an RC circuit, and then using the knowledge we just learned. So here it says determine the power factor for an RC circuit with R equal to 4 and C equal to that 0.35 micro farad. So R is 4.0 kilo ohms. Okay, that is connect to an AC generator with an RMS voltage of 24 volts and a frequency of 150. Okay, so you're looking for power factor. So that means you are looking for the cosine phi, which is equal to R divided by Z. Okay, it gives you R already. You need to figure out Z here. Doesn't seem like you need to use the RMS voltage here. Okay, you guys can give that a try. Now it's asking you, will the power factor for this circuit increase or decrease, or stay the same if the frequency is increased in part B? Okay, you can also address that. I'll give you guys a couple of minutes to work on this, and then we can take a look on this together after that. Okay. All right, so I think we can take a look on here. So we are given R, we can just need to find out Z. Okay, Z is for an RC circuit, Z is equal to R squared plus XC squared. Okay, and XC is omega 1 over omega divided by C. So we can do that 4.0 times 10 to the third ohms square, and then plus. So this would be 1 over 2 pi times F. It tells you the frequency 150 hertz, okay? And times the C, this is going to be, yeah, I'm running out of space here, but Yeah, put C there. This is 0.35 times 10 to the minus 6 farad. Okay, so remember that's farad. And then you want to square everything in the denominator over here. Okay, and then take square root of everything. All right. So it will tell you your Z is about 5.02 times 10 to the third ohms. Okay. Then you can calculate what's your power factor of cosine phi. That is 4.0 kilo ohms times 10 to the third ohms divided by 5.02 times 10 to the third ohms. Okay, gives you roughly 0.80 as your power factor of this RC circuit. Okay. Um, any questions you guys might have? All right. If not, then so let's see. Part B says, will the power factor for this circuit increase, decrease, or stay the same if the frequency is increased? Okay, so you can kind of rationalize this. So if your frequency, which is this guy, right? If this increase, so then this thing, 1 over of this thing, after you square the denominator will decrease, right? So the overall Z will decrease, okay? If your Z decreases, then R is the same, so power factor will increase, right? So you can kind of rationalize that way. So you can say your power factor will increase if the frequency increases, okay? All right. You can let me know if you have any questions. Okay, you can speak up after you unmute yourself. All right. If not, we'll move on to take a look on the phases for inductor and resistor in the circuit. Okay, so if you have a resistor and inductor in the circuit, now the current, because they are in series with each other, so current will be the same. Okay, so the current, this is the current for the current phasor for the resistor, and then this is the voltage phasor for the resistor, and then this is, should be also the current phasor for the inductor because they are in series. Okay. However, the voltage phasor is different because voltage leads the current by 90 degrees. So then you are ahead by 90 degrees in that case because your omega is going in that way. Okay, so your voltage is over here. So you can see again the voltage phasor on the inductor and then voltage phasor on the resistor, they are having an angle of 90 degrees, right? So then for the overall voltage phasor for the whole circuit, V max, that should be, according to Pythagorean theorem, should be square root of R squared times XL squared, okay? And there's a common factor of I max that will cancel out. Okay, so this is similar. You can follow this the same as you when you did the RC circuit. Okay, so basically you'll start with like V max for the whole circuit is equal to the I max times R, the term square, and then the I max times XL square. Okay, so then the I max is the common factor there. You can single it out, but it turns out that the Z in this case will be equal to R squared plus XL squared, where XL is the inductive reactance, which is omega times L or 2 pi F times L, okay? So similarly for power factor, you can calculate for RL circuit will be also R divided by Z, which is equal to R divided by square root of R squared plus omega L squared, okay? And so the currents in resistor, capacitor, and inductors are as a function of frequency. Okay, you can see. So for resistor, if this is a circuit only has a resistor, then it's going to be just a constant, right? It's just because it's equal to V divided by R. they are in phase, and then this is will be constant. Now, if you have a RC circuit, okay, so you can see the current. If we go probably a couple slides back, let me see. On here, okay, so you can see current it's equal to V divided by the square root of this, okay, or maybe let me show you on my paper here, it should be easier to see that. So for RC circuit, okay, so your IRMS is equal to your VRMS divided by the Z, okay. So if you have maximum already, then the RMS quantity will be fixed, okay. And that's equal to VRMS over square root of R squared plus XC, which is 1 over omega C squared, right? So you can see if you have RC circuit, as your frequency goes up, okay, so then this thing goes down, all right? So then your current will go up, okay? And then you will reach a plateau because when this omega is infinity, then this term is 0. Okay, you reach the plateau of the resistor only, which is V over R. Okay, for your RL circuit, your IRMS then will be equal to similarly V RMS over Z, but in this case, your Z is equal to square root of R squared plus omega L squared. Okay. So then if this increases, then your current will decreases down to 0. Okay, if your frequency is very high, infinity large, okay, then it's approaching 0 in that sense. Okay, so that's what this plot is about. All right, so let's take a look on one example here on the RL circuit. So this one says the RMS current in an AC in an RL circuit is 0.26 when it's connected to an AC generator with frequency of 60 Hertz and an RMS voltage of 25 volts. Given that the inductor has an inductance of 145 millihenry, what's the reactance? What's the resistance of the resistor? Okay, so this is given. You're looking for the R, and then find the RMS voltage across the resistor. Find the RMS voltage across the inductor. Use your result from part B and C to show that RMS on the resistor square plus RMS on the inductor square is equal to 25, or square root of that is equal to 25. Okay. All right, so let's see here. So if you want to calculate IRMS, you'll be doing VRMS divided by the Z, okay, the impedance of this RL circuit. So it tells you the IRMS, okay, and then it tells you the VRMS. So you can calculate Z from there. And then Z is also equal to square root of R squared plus omega L square. Okay, so this is the XL reactance of inductor. So L is given, so you can calculate this guy, and then frequency is also given. Okay, omega will be 2 pi times the frequency. Okay. All right, so let's do it this way. We'll calculate what's Z first. So Z then will be equal to V RMS over I RMS. Okay. So that's 25 volts divided by 0.26 amps. That gives you 96.15 ohms. Okay. Then we can plug the number in there. So Z, that's 90.15 ohms equals to square root of that. So you can do square to get the square root of it. Okay, so you can square this term. Then that's equal to the R square plus omega L square. Omega will be 2 pi times frequency, the 60 hertz, times L, it's 145 times 10 to the minus 3 Henry, okay, squared. You can solve for your R, okay? All right, so if you solve for your R, I think you guys all know how to do this. So I'm going to just give you your R value here, 79.1 ohms, okay? So that's your R. And then if you want to keep just 2 sig fixed as the other numbers given in the problem, you can say 79 ohms, okay? So that's your part A. Your part B is asking you what the RMS voltage across the resistor, okay? So to do that, V RMS R will be similar to Ohm's law, but you'll be doing RMS quantities, okay, times R, okay? So it's the 0.26 amps times the 79.1 ohms, okay? That will give you about 20.6 volts, okay? Or if you say 21 volts. Part C is asking you to find what's the RMS voltage across the inductor. All right, so V RMS on the inductor then will be equal to I RMS times the inductance of it, right? Our reactance of the inductor. Okay, so we have 0.26A again. This guy, XL will be equal to 2 pi again times the frequency times the 145 times 10 to the negative 3 Henry. Okay, so that's giving you 14.2 volts, or you can say 14 volts on that. Now part D is asking you to show that square root of VRMS on R square plus VRMS on the inductance square is equal to 25. Okay, so you'll be doing 20.6 square plus 14.2 square and then square root. Okay, and then it's exactly 25.0 volts. Okay. Any questions you guys might have, just let me know. Okay. All right. So if you are clear, we'll move on. Now, if we have the 3 different elements at the same time in a AC circuit, so we will put them in series with each other again. Their current phases should be the same because they are in series. Okay. However, because of you have a capacitor and inductor here, those two, they do not have voltage peak at the same time as the current. Okay, so let's start with, say, the green I max is the current maximum in the circuit. So then that's the current phasor for the whole circuit. So the vector voltage vector or phasor for the resistor will be in the same phase as the current, right? Overall current. So that's that yellow one. And for the capacitor, the current is leading the voltage. So then its voltage phasor is this red one. Okay, in this case, it will be I max times XC. However, the inductor, the voltage leads by 90 degrees. So it will be that blue arrow there. Okay, so then the overall, we'll be adding those three vectors up, this red one, and then this blue one, and this yellow one, and this blue one up. Okay, so you can see the blue one and the red one, they are in opposite direction, so you can actually subtract one from the other. Okay, so this will give you I max XL minus I max XC in the pink, in the purple here. All right. So then purple and yellow is having a 90 degree. So then overall phasor for voltage phasor would be this brown one here. You can use Pythagorean theorem again, would be R squared plus XL minus XC squared to get that. Okay, so then this is the overall impedance for an RLC circuit when you have them in series with each other. XL is omega times L, and then XC is 1 over omega C. Okay. So once you have the impedance of the whole circuit, then you can do V RMS divided by the Z to get your IRMS in that case. Okay. So for the phase angle in this case, okay, if you take a look on the previous slides over here, that's this angle phi. That's the angle between the current and then the current phasor and the voltage phasor for the circuit overall. Okay, so this I and then this V max. So if you are doing tangent of max, then it's the XL minus XT over R. Okay, the same thing here. So the angle between the two, right? There's two vectors or phasors, I max and then V max. Okay, that will give you the power factor cosine phi that will be equal to R divided by Z. Okay. And in the case of XL equal to XC, then the phase angle will be 0. And then because those two XL and XC will cancel out, okay, then you only have the effect of R. Okay. All right. So let's take a look the example on the RLC circuit here. So it tells you the R is 8.8 kilo ohms, your C is 0.12 microfarad, and your inductance is 28 millihenry. Says the generator supplies an RMS voltage of 115 volts at frequency of 60 hertz. What would be the RMS across each, or RMS voltage across each element? Okay. So to find the RMS voltage across each element, you will have to find the RMS current first. And then you can do the RMS current times R to give you the RMS voltage on the resistor, IRMS times XL for the voltage across the inductor, and then IRMS times XC for the RMS voltage across the capacitor. Okay, so I think the logic is simple here, but just a little bit algebra to play around. Okay. You guys can give it a try, and then we can take a look on the solution together in a couple of minutes here again. All right, so let's take a look on this one together. So to calculate the RMS voltage on each one, so for example, for a resistor, you need to do RMS, the current, times the resistance, okay? And then for RMS on the inductor, you'll be doing RMS times XL, okay? And then VRMS on the capacitor is going to be IRMS times XC, okay? So it looks like we need IRMS, then also IRMS, you can calculate from VRMS divided by Z. So we need to know Z, okay? And then Z is equal to square root of R squared plus XL minus XC squared, okay? So think we can calculate the XL and XC first, so we can calculate Z, and then once we have Z, we'll have our IRMS. Okay, and then once we have IRMS, we can calculate the voltages, RMS voltages. Okay, so let's do that. XL, let's calculate XL. XL is equal to 2 pi F times L. Okay, so that's 2 pi times the frequency 60 Hertz times L. It's given as 28 times 10 to the minus 3 Henry. It's millihenry. So that gives you 10.6 ohms, right? And XC, you can calculate, it's 1 over 2 pi F times C. So 2 pi, or 1 over 2 pi times 60 Hertz times the C, which is 0.12 times 10 to the minus 6, okay, farad. That gives you, this is a relatively big number, 22.1 kilo ohms, okay, times 10 to the third ohms. All right, so then after that, you can calculate your Z is equal to square root of R is given as 8.8 kilo. Okay, so 8.8 times 10 to the third square and plus 22.1 times 10 to the third ohms minus 10.6 ohms, okay, square. This one gives you 23.8 times 10 to the third ohms. That's your Z. Now you can calculate what's your IRMS. Will be equal to VRMS over your Z. So your V is 115 volts divided by your Z, 23.8 times 10 to the minus positive 3 ohms. That gives you 4.83 times 10 to the negative 3 amps. Okay. So your IRMS, then you can calculate the 3 RMS voltages asked here. So V RMS on R is equal to IRMS times R, 4.83 times 10 to the negative 3 amps times the R, the 8.8 times 10 to the third ohms. Okay, that will give you 42.5 volts. The VRMS on the inductor is the IRMS times XL, 4.83 times 10 to the minus 3 times 22.1 times 10 to the third ohms. So that's that guy. And that gives you, or actually, this is C. This is XC. So let me just change it to C here, XC here. Okay. So that would be 106.8 volts on the C. On the L, IRMS times XL. So 10.6 ohms on that. That will give you 0.0512 volts. Okay. And at the end, you can verify that if you, so for your VRMS, okay, it's going to be equal to, you are done with this over here. But if you want to calculate your VRMS, which is 115, that should be equal to square root of VRMS on the R square plus, and then the difference between these two, VRMSL minus VRMS on the C square, okay? Just double checking on what you get. So 42.5 square plus 0.0512 minus 106.8 square, and then square root, okay? That's going to be just exactly 115, okay? All right. Any questions you guys might have? All right, if not, because you guys are having exam tomorrow, so we'll just stop here for today, okay? And then I'll see you guys tomorrow for the exam, and then some of you guys for this afternoon for the lab, okay? See you guys, bye.
Thank you. Have a great day.
Bye, you too.